Good morning. Welcome to part 13 of RevSim's virtual coffee break series. Today we're going to talk a little bit with Wolfgang Gintz of the Uber Cloud about CFD analysis. Wolfgang's got a case study he's going to take us through. And kind of important to note that these are very quick walkthroughs of these different topics on the virtual coffee break series. And you can get more information, you'll see at the end of this presentation where you can find that from on RevSim.org as well as from the various presenters. RevSim.org quickly. If you're not yet familiar, I invite you to visit the site. There's an opportunity for you to learn more about some of the different disciplines within the engineering and product development democratization push that's going on. Also, we've got a newsletter that I invite you to sign up for, and it comes about once a quarter. You'll get always be updated that way. If you haven't yet joined the RevSim community, I invite you to do so. You'll be joining a list of other users like yourself, simulation providers. There's a host of companies involved, a host of individuals, as well as some academia and industry analysts. It's just a community that's driven with a common goal to democratize simulation. So with that, I'm going to turn things over to Wolfgang, and he'll get right into the case study today.
Yeah, thank you, Bob. So this case study is about the intake manifold of an automotive engine, which is a critical system, as careful design of this component for pressure drop directly relates to the engine's efficiency. In a V6 manifold, it is also important to achieve a uniform flow rate across each of the branches of the intake duct. The flow analysis in this case study using CFD simulation software provides a thorough understanding of these parameters and helps in designing efficient and economical manifolds. So in these two figures here, on the left side, you see the fluid domain of the intake manifold, which has to be prepared for the simulation with, we'll get back to that later, but with the right subdivision of simulation regions, domain decompositioning, and also over something like 3 million cells. And on the right side, you already see one of the results, which here is the velocity path lines inside that manifold. So the critical thing here, as I already mentioned, is the pressure drop, which directly relates to the engine efficiency, and the uniform flow rate, which has to be achieved across each of the branches. So CFD flow simulation provides a deep understanding of these and several other parameters, which we see on the next slide then. But yeah, so this steady state incompressible flow analysis is to evaluate the quantity of airflow to each outlet and estimate the pressure drop there. The model was created and discretized with tetrahedral and prism elements. So tetrahedral you usually use within the flow field, and the prisms you use to get a more accurate resolution on the boundary of this geometry. And Star CCM Plus has been used and it's hosted in an Uber Cloud CAE container. And this case study, again, here you can access through this Uber Cloud website link to our compendium number 4. Okay. Yeah, thanks. So again, a result here is presented in the figure on the left side, which is the pressure contours at the cross section, which you see in this very little image on the right upper. And you see that these pressure contours at these sections, in the 6 branches, are relatively close together, which is a good result here. There's a very nice quote from the the engineer at CAE Technologies Incorporated, Krishnan Nayanar, and he says excellent performance of the star CCM container, eliminating the need to have all software in-house. And the HPC cloud provides packaged software ready to go for fast analysis and so on. So he was very excited to get access to a much larger environment on Microsoft Azure Cloud using Azure A9 compute instances, and you can select there any instance which fits your problem nicely. So here we put together a 10-node HPC cluster with 8 nodes, dual sockets, CPU E5, etc., and quite a bit of RAM, altogether 1 terabyte. So ready for a big project, for a big problem and geometry. And the beauty with that cluster is it's connected or interconnected with 40 gigabytes InfiniBand, and to basically avoid the hypervisor's latency on these Azure compute nodes, you have something which I usually call, bypassing the hypervisor through what they call direct memory access, RDMA. And the software, as I already mentioned, for simulation was star CCM Plus, version in this case 10.04, and the simulation took about 10,000 iterations until all monitored parameters like mass balance, velocity, pressure are stabilized. As I mentioned before, so the mesh had more than 3 million cells and 5 boundary layers, which is the layers between the solid structure and the inner of the flow field. And that one is, to prepare everything in the computer, then simulate or building up this geometry took 17 minutes, and the total time to run these 10,000 iterations for quite a large problem was just 5 hours. Okay, so that was about the case study, and we like to invite you to learn more about Revolution in Simulation, where you can register or just go to the website. And our case studies you find easily at OSC, which you can contact under this link, and also on UberCloud's a compendium link, which I just mentioned 3 slides ago, or you directly subscribe to our monthly newsletter, which usually contains 1 or 2 of these latest case studies. So with that, we thank you very much. And this was Bob Farrell, Wolfgang Gensch, and Alan Jocker, and we are looking forward to meet you again at our next coffee break webinar. Thank you.